Welcome to the lesson on problem statements. This is part of the unit mass transfer, which is being taken up as part of the NPTEL MOOC on transport phenomena in materials. There is a procedure to solve problems in mass transfer explained very well by David Wilkinson in his book titled Mass Transport in Solids and Fluids. First, we have to start the procedure by identifying the problem, that is, to remove extraneous information and write down what exactly is the problem being asked. And then we identify the desired inputs and outputs. That is, basically we are making the problem a well-defined problem from an ill-defined situation. Identify the physical mechanisms. Target the precision. By this we mean to what accuracy we need the output. And then construct the model. This involves drawing a schematic of the problem and putting down equations that are relevant along with the boundary conditions, and then coming up with a solution. Once the solution is available, we then interrogate the model. By that what we mean is we check if the solution is self-consistent. Does it give useful answers for slight variations in the inputs? Once this is done, we can say that we have solved the problem within the description that is available to us. So there is a method to go about, and that we discuss now. So first we have to come up with a geometry of the problem. So we have the luxury of taking the planar geometry, which becomes very easy for us to solve. But there are some situations where it could also be cylindrical in geometry. We have to also have some judgment about the geometry being planar or cylindrical based on the radius, whether it is large or small. If the radius is small, then we have to stick to the cylindrical geometry. If it is large enough, then locally it can be assumed to be of planar geometry. Similarly, the geometry sometimes can be spherical, in which case the equations and the solutions will be specific to the spherical geometry. And accordingly, the governing equations have to be picked up. So shortly we will see the governing equations, the different terms which will be different for the three geometries, namely the planar, cylindrical and spherical. Once the governing equations are written down, then the terms in the governing equations can be chosen depending on the number of dimensions that our problem has. Very often for a textbook problem or a problem that we should be solving with pen and paper, then it would usually be a 1D problem. So it means that we have one term alone in each of the expanded terms in governing equation. And if the problem is such that we have to take a two-dimensional situation, then there will be two terms, which means that we may then go to a numerical way of solving the problem very often. And real life situation, we would have it as a three-dimensional problem, and we would usually resort to a full computational solution with a program that will help us in the solution. The governing equations have to be written for species, the composition of the species that is to be solved for, and we have to write as many equations as the number of species. So the number of species that are participating in the problem is to be identified. Very often for a textbook problem it will be only one species, but when there are more than one species, then we have to also inspect whether there is a coupling between the species. It could be sometimes that the two species are moving in such a way that the medium is stagnant, in which case the problem becomes slightly simpler for us to address. Then we have to also come up with some assumptions which will reduce the number of terms in the governing equations. And these assumptions can be, for example, it's a steady state problem. This we would know from the problem description and the keywords such as after a long time or over a long duration. If such terms are appearing, then we may actually imagine that the problem can be taken up as a steady state problem. And very often the governing equations are to be applied for a solid state of the domain, which means that we may actually take the advective term to be negligible. Then often we have mass transport problems where there is no reaction, which means that there is no generation term in the governing equation. And as we have seen, if there are number of reactions that are possible, then the generation term will be actually a summation. So the entire term can be neglected if we assume that there is no reaction happening in the domain. And so by this way we reduce the number of terms in the governing equation, and we have then written the governing equation for the number of species, and then we have also reduced the terms in the governing equation for the number of terms, and chosen the geometry correctly and made the assumptions that are relevant. So we now have equations that we can actually go ahead and solve for. And once we have that, then we have the possibility to complete the solution by looking at the initial conditions and the boundary conditions. So the governing equations that we have derived in earlier lessons are as follows: the Fick's first law and the second law that are to be used in mass transport in a generalized fashion that we have derived, and they are as follows. The flux term is given with the following expression: Ji star is minus d nabla Ci. That is basically the diffusive flux is down the composition gradient. We have already seen under what assumptions this is valid. The star actually indicates that it is diffusive flux and not the total flux, that being when we have the advective velocity of the domain also taking part. The flux term is basically indicated here in green color, and we can then expand it for the particular problem that we have at hand, namely for the geometry and for the dimensions that we require. So by writing the operator, gradient operator, we have the flexibility of expressing in a way that is not bound by either planar geometry, cylindrical geometry, spherical geometry, or 1D, 2D or 3D. The governing equation which we derived is given here with the 4 terms. So what we do is that the second term on the left hand side we expand, and then we assume that the domain is comprising of a fluid which happens to be incompressible. Then we can indicate that with the form which is very commonly seen in this particular subject, namely the convective diffusive generalized equation form for the mass transport, which is given in 4 terms. These terms are then indicated as follows. The first term is called the transient term, which tells you the way time is actually affecting the composition. So when we have a steady state assumption, then the first term can be neglected. The second term is called the advection term, where we have the advective velocity u that is coming in, and if we take the domain to be solid, then we can actually neglect the advective term. The third term, which is the first term on the right hand side, is called the diffusion term. This actually we have modified by taking the diffusivity out of the grad operator, which means that it is not a location dependent property, and this is the term that is most important in arriving at the distribution of the composition as a function of distance. The last term on the right hand side is the source term or the generation term, which comes in because of reactions that are taking place, and in situations where there are no reactions, then this term can be neglected. So like this we are able to identify in the governing equation in a general form what are the terms that can be neglected for what kind of assumptions. So let us look at how the flux term will be different for different scenarios. So for the planar geometry, the flux term is expanded here where the gradient operator is expanded. So the I, the subscript I, indicates that it is for the species I, which means that as many number of species that are there in the domain, we have to write those many diffusive fluxes. And the right hand side, it has the three terms which are basically the gradient components along the three directions. Of course, if it is one dimensional, we have only one of the three terms that are present. In the cylindrical geometry, the diffusive flux is given in slightly different manner. You could see that here we have got the term along the theta direction, which will be slightly different from the way you have written it for the radial and for the axial directions. So accordingly, you have to take the terms when we are looking at a cylindrical geometry for the flux. The spherical geometry, the term is appearing as follows. For the spherical geometry, you can see the diffusive flux for the species I given in this form along the r, theta and phi directions, which are basically with the components given here. You can see that it's appearing with r d theta and r sin theta d phi, which we have to take care when we are estimating the fluxes in the respective directions. Very often in spherical geometry, we are interested in only the radial flux, and therefore the very first term alone is sufficient for most of the textbook problems. Coming to the advection term, in the planar geometry, the advection term is quite simple. You could see that it is written with the three components of the velocity along the three directions. We would usually find use for this when we have a moving coordinate system, and the one of the directions would be sufficient, and therefore one term of this term is sufficient for us. The cylindrical geometry would have the advection term, which will have the velocities along the radial, the theta and the z directions. And in the spherical geometry, which is very rare for us to experience, and that would have the advection term with the velocity along the r, theta and phi directions. The diffusion term is the most important. This is what we would actually be integrating to arrive at the solution, and that is basically also referred to as the Laplacian. And so you have the Laplacian for the composition of species I written as a summation of three terms that are given here, and usually in one dimension you would have one of these terms that would be required. In the cylindrical geometry, usually that also is quite common for us in solving, and we would usually have only one of the three terms that will be active, because the problem will be given usually in a one-dimensional assumption being possible. So you have one of the three terms on the right hand side being used for the diffusion term, and for the radial diffusion you see that its appearance is like this, which means that we need to basically integrate this term when we are deriving the composition of species I as a function of r. And for the spherical geometry, which is also not very uncommon, usually the radially outward diffusion of species I is considered, and for that the very first term is what is important. So this term is important, and the remaining terms are very rarely used in most of the problems in the undergraduate level, where we are trying to solve the problems on a pen and a paper. So the diffusion term has to be picked depending upon the problem description, and we are underlining the terms that are sufficient for most of the situations that we encounter in numerical problems. Very often we are given a problem description where the units of the quantities that are given to us are not readily useful for the equations we have written. So we have to remember that the composition that is used for the diffusive flux term is to be given in concentration, that is mass per unit volume, and often we will have weight fractions or weight percentage that are being given. So the way we convert that is by the following equation as described in the book by Wilkinson. We have all the conversions that are neatly described there. So you have the concentration of the species that is diffusing, let us say hydrogen in solid nickel, and you would write that as the kgs of hydrogen per meter cube of the solid nickel, and that has to be then expressed in terms of the weight fraction into the density, and the weight fraction can also be converted from weight percentage by dividing by 100, and the density we mean by the density of nickel, because that's a matrix in which the species hydrogen is diffusing. So if you have, for example, 0.01 weight percent of hydrogen diffusing in solid nickel, then the density of nickel is 8790 kg per meter cube. So you would get the concentration as 0.879 kg of hydrogen per meter cube of nickel. So that way we can actually convert the units and use. So you have also units sometimes given in terms of the molar quantities. So sometimes we can also work with the concentration in moles per meter cube, which means that the diffusive flux will also be in moles per meter square per second, and then we can relate them to the mole fractions, and molar volume will be coming into play there, and the molar volume will then be available because it's a thermodynamic property. We also have sometimes the conversion of units required for the phases also, not only for the species, for the phases also. So here is a conversion factor where the volume fraction of the phase, ith phase, there are several phases that are part of the domain. So volume fraction of the phase is related to the weight fraction of the phase through the average density of the alloy and the density of that particular phase. And we also have relationships that govern the different volume fractions and densities of the phases, giving us the average density of the alloy in the following manner. So we can use these to convert whenever the weight fraction of a phase is given or volume fraction of a phase is given, and we are supposed to make assumptions to convert the units. Now, choosing the domain, one of the quantities that is very important for us to realize is the diffusion length. By this, what we mean is how big is a domain with respect to the length over which the diffusion is taking part. So when we have the diffusivity available as a number and also the time roughly over which the diffusion process is taking place, then we have the diffusion length readily available using this formula LD is equal to root of dt, and we can then substitute to get the diffusion length in terms of meters. So if you have diffusion of hydrogen in iron at 298 Kelvin, the diffusivity value is 1.6 into 10 to the power of minus 10 meters square per second, and if you were to look at for 1 minute of the diffusion process, then LD will come to be roughly about 100 micrometers. Okay. And usually if the domain is about 3 times as big as the diffusion length, then we can assume the domain to be infinite, that is the length is very large. So which means that for the case of hydrogen diffusion in iron at 298 K, as we have seen, the for 1 minute of diffusion process it would come to 100 micrometers, which means that if you have a domain of about a millimeter, then it's as good as a infinite domain. For a non-rectangular domain, usually we have to also see how does the radius of curvature compare with the LD. Is the radius of curvature significantly large compared to LD, in which case we may actually take the planar geometry to be valid. And wherever possible, we should try and see if the rectangular semi-infinite domain is possible. The reason being that there are a lot of solutions that are readily available for this particular kind of a domain. So semi-infinite domain, if we are able to bring the problem to, then our life is quite simple. And always remember that the diffusivity is actually a function of temperature. We will have a discussion about this shortly, because the temperature at which we are having the problem has to be always known, because we have diffusivity determined as a function of temperature, and from that only we can actually say what is the LD, and then we can make the rest of the assumptions. So how does the temperature dependence come about? So diffusive processes are basically activated processes, and therefore they would follow the Arrhenius kinetics, and therefore you have the diffusivity expressed as d naught into exponential minus q by RT. Sometimes the numerator can be given per atom, in which case the denominator is not R but the Boltzmann constant K. So we can inspect the units of the activation barrier and accordingly pick the equation. So we have got Q by RT. Q is the activation energy for the diffusion process, and the values of D naught and Q are tabulated in handbooks, and one such handbook which we normally refer to is the Smith's Metals reference book. So from there we pick up, let us say, the diffusion data for copper in aluminum matrix, and then plot. So you could see that if you normally plot diffusivity as a function of temperature, then it would actually be very odd, because it would be 0 for most of the axis, except at the highest temperature there is some variation. But if you plot it with the semi-log y, that is, along the y-axis you have got the logarithmic scale, whereas along the x-axis you have the normal scale, then you can actually see the variation, that the diffusivity will come down in orders of magnitude as the temperature is decreased. So you can see from here that as the temperature is decreased from 900 Kelvin to 600 Kelvin, the diffusivity has come down by a factor of 10,000. So that's quite a large variation that is coming from the activation barrier, the magnitude, and depending on that, this variation would be different. And to just know how important it is for us to keep the temperature information, I'm illustrating here by using this blue color map, where we see that the diffusivity will come down from 10 to the power of minus 14 meter square per second to 10 to the power of minus 15 meter square per second if the temperature were coming down from 720 to about 660 Kelvin, which means that within few tens of Kelvin the diffusivity can come down by a factor of 10. And now that's significant, which means that when we measure the temperature in the experiments and say that plus or minus 10 Kelvin is the accuracy, then it actually implies that the diffusivity values changing by about 100%, that is factor of 2, and that's quite significant when we plug in the numbers later on. So we have to be very careful with respect to these estimates because of the sensitivity with respect to the temperature. Now we have already come across the concept of point effect of diffusion while discussing the thermal problems, and there we said that when we look at the flux term, it actually will be dependent on the geometry, and for the three geometries, spherical, cylindrical and rectangular, we have written down the flux term. The same flux is also can be applicable for also the mass transfer, except that it is the flux of this species that we are describing. And usually the concept of point effect of diffusion is that it is proportional to the extent of space that is available, and which means that you can actually assume the domain to be rectangular provided the radius curvature is large. So which means that by estimating the temperature at which the process is happening, and then the diffusivity relevant at that particular temperature, and then the length, diffusion length at that particular scenario, then you can see whether the radius of curvature is large or not. Accordingly, then we can pick the geometries. If the radius of curvature happens to be very small, then we will be forced to keep the geometry and choose it to be cylindrical or spherical as the problem requires us to. So here are some examples. So for example, you have carburization of a gear that is usually done. So you have problems that are given in most of the textbooks about the diffusion of carbon in steel, and those are the problems where you can actually take a planar case, though the gear is nothing like planar. It has a lot of features and curvatures, but then the size of the gear actually helps us in knowing that a planar assumption is quite reasonable. And I have taken the images from Wikimedia. On the other hand, let us say that if you are solving for the composition distribution while an alloy is growing as a rod eutectic, then because the dimensions of the eutectic spacings are very small, it will be in tens of microns, then what happens is that you are forced to take the cylindrical geometry for this particular diffusion. So you can see that going from the gear, which is at the scale of centimeters or even more, to a eutectic, which is basically at the scale of a micron or 10 microns, we are actually having a situation to choose the diffusion term either as planar or as cylindrical geometry given by the problem. So the scale of the diffusion process is very important. And there are some problems where we have the degassing using the argon bubbling, and the domain normally will be at the interface between the bubble and the liquid metal. So you do have the bubble, which is actually spherical, and it is increasing in size as it is going upwards. However, at the interface between the bubble and the liquid metal, you can take a small rectangular domain and then assume that to be reasonable and solve, because we see that the diffusion when we plug in the numbers would make that possible. And there are problems that are to do with the diffusion couples, where we have got two metals that are actually kept touching each other and then held at high temperature, and we are interested in the diffusion profiles across. And these are also the problems where we have the planar geometry that will be very reasonable for us to assume. And oxidation of metallic alloys during hot corrosion is also one of the problems that is very important in mass transfer, and there also planar geometry is very often used. So as we now look at, the subjects are as follows. In mass transfer, we will have examples coming from process metallurgy, where we have problems like degassing and reactions that are taking place. So we do have problems that are involving mass transfer in process metallurgy using these kind of scenarios. In physical metallurgy, we have mass transfer appearing thanks to the diffusion process that is inherent, and in heat treatment it is very common. And in heat treatment you have got homogenization that is very important, particularly in multi-component alloys, where the temperature choice and the amount of time etc. are quite critical, and that's basically a mass transfer problem. And you also have in heat treatment precipitation happening, and that's also a mass transfer problem, where actually the elements are segregating to form some compounds, and the diffusion profiles will start making a very big difference to the way the precipitation kinetics are going to take place. And during additive manufacturing, you do have actually heat treatment coming up, because after the part is printed, you usually subject it to heat treatment for stress relief or precipitation, and so the entire physical metallurgy problems related with mass transfer are also applicable to the domain of additive manufacturing. You also have some other phenomena that are important. For example, in powder fed additive manufacturing, the mixing of the different powders in the melt in the short amount of time available for that droplet to solidify, you do have the mass transport that is playing a role. In additive manufacturing, we also have scenarios where selective evaporation is going to play a role, because very often the vapor pressures are different for different elements, and that sometimes leads to selective evaporation. So often the powder mixture has to be fine-tuned, so that taking into account selective evaporation, you still get the deposit of the alloy of the desired composition. During welding, which is a process that is actually can be called as the process from where the additive manufacturing was born, you could actually think of it where the mixing is very important, because often we have the weld consumable different from the base material. So how would they mix in the weld pool? That would actually again be a mass transport problem. And often we talk about what is called dilution effect, which is basically the way the deposit or the weldment is having different composition compared to the base material, and that is because of the mixing, and this plays an important role in the properties of that weldment, and that's also a mass transport problem. And you also have segregation taking place in weldments because of solidification process that is undergoing in the fusion zone once the heat source moves away, and that's also a mass transport problem. Segregation is also relevant in additive manufacturing because you have got powder droplet by droplet solidification, and the segregation at that scale sometimes is very important for the precipitate distribution. Casting is also a process in which segregation plays a role, and so mass transport, you can see that is playing a role in casting also. And in hot corrosion, I have mentioned earlier, you do have the growth of oxide, which is basically a mass transport problem. So you can see that the subject mass transfer is playing an important role across metallurgy, from process metallurgy to corrosion, welding, casting, additive manufacturing, and physical metallurgy. So which means that it plays a role in the entire subject of metallurgy. Now the dimensionality of the problem should be decided, and you have got the 3 dimensions possible: 1D, 2D, and 3D, and very often 1D is sufficient, but sometimes even in 2D or 3D problems, by taking into account the axis symmetry, you can reduce the dimension. So you can have a pseudo 1D even though the actual dimension can be 2D or 3D. So the number of species is important. If you have only one species that is dominant, playing a role in the mass transport, then a single species equation should be sufficient. If you have a binary, then that means that there are 2 species that are playing a role, and a coupling between them would be very important. And very often in a real life situation, you have a multi-component domain, so we have multiple species that are participating. The number of phases also important. Very often in the numerical problems at the level of a undergraduate textbook problem, you usually have only a single phase that is in the domain. So the domain is comprising of a solid or a liquid or a gas, and you do not have any other complication. However, in a real life situation, you have 2 phases, and which actually makes it difficult for us to solve by pen and paper. So usually you have a simulation of the process being done for us to understand how the mass transport is happening across the 2 phases. And in a complicated process, in process metallurgy, typically you will have all the 3 phases that are participating, and it becomes a multi-phase problem. And multi-phase problems are notorious for their complexity, and numerical simulations are today the only way that we can gain insights into the mass transport happening in such scenarios. The initial conditions are important for us to solve the problems, and very often the composition profile in the domain is specified at time is equal to 0, and that's the initial condition, and usually it's a constant composition that will be given. So you have the entire domain to be at a particular value of the composition or concentration of a species, and that is available to us very often. And sometimes what happens is that the initial condition is actually segregated domain. That is, for example, after solidification, after additive manufacturing, there is some segregation of elements in the domain that we are looking at, and we are looking at, let us say, homogenization process. In such case, the initial composition profile is actually a segregated profile, and it can be assumed to be having some ups and downs that has to be obtained from the experiments. And sometimes it is possible for us to express these segregations as a sum of sine and cosine functions thanks to the Fourier series that we can apply. So the Fourier theorem can be applied, and we can actually convert these random segregations into very regular sum of a finite number of sine and cosine functions, which makes it very easy for us to estimate the homogenization times, as we will illustrate later on. So sometimes we can actually even approximate a segregated profile to be just 2 different values, and then you can actually make that to be a sum of cosine functions, let us say about 10 such functions, and then we have ability to then use the theorems available for homogenization to estimate what would be the time taken. So the one with the largest amplitude and wavelength will be important for us in understanding how the homogenization is done. So it's not obvious that the initial condition is very simple. Sometimes it requires some experimental measurements to calibrate and arrive at what is the initial condition. When it comes to the boundary conditions, we have a lot of variety. So I am here putting all the boundary conditions that are seen in a typical textbook on mass transport in one slide, so that we can come back to this slide whenever we require to identify what would be the relevant boundary condition. So usually the boundary conditions are specified either by flux or by their value, and when the flux is specified, then you have that to be specified to be 0, and that would be quite good, because it means that there is no mass transport across that particular domain boundary where the 0 flux has been specified, which means that the concentrations are going to be flattened out at that particular boundary, because 0 flux means that 0 gradient, and which means that the slope of the concentration profiles will be flat, that will be horizontal when we plot them. Sometimes the flux is also specified to be constant value, and this is a scenario where you have deposition from a vapor to form a particular layer of a compound, and there the flux is available because the rate at which you are actually sending the particular species will be available, and you can then use that for the constant flux. So for the CVD processes, this particular assumption would be quite commonly applicable. Often mass transfer coefficient is also be used for the flux. So this is an analogous process to the heat transfer coefficient by the Newton's law of cooling. Something very similar can be used also for the flux. And the mass transfer coefficient can then be made available because we have different models like the Higgs model or from the Sherwood correlations, or they are also derivable by knowing what would be the composition profile if it was available analytically for us. When the value is specified, then we have to get those values of the concentrations or compositions at the boundary from either phase equilibrium or reaction equilibrium. So when we have the phase equilibrium, then you have scenarios, for example, where the solubility limit is giving us the value of the concentration at the boundary, and sometimes it is also available because you have the chemical equilibrium that is giving us what would be the compositions. And reaction equilibrium is very similar, where we have a gas that is actually getting adsorbed into the metal at high temperature, and then that is leading to the flux. Then usually Sievert's law can be applied, and in a very generic sense you can actually express the equilibrium constant for the particular reaction and use the equilibrium constant to arrive at the value of the composition at the boundary. You can actually see that Sievert's law is nothing but a special case of a very generic equilibrium constant being used for a reaction equilibrium at the boundary. These concepts are very well described in the book by David Wilkinson, the book titled Mass Transport in Solids and Fluids. You also have very generic problems about mass transport in the book by Welty, Wicks, Wilson and Rohrer. This is actually a very comprehensive book, but it gives the treatment of the subject quite amenable for the mechanical engineering audience, and the subject is dealt in a manner that conveys the uniformity across the momentum, heat and mass transport. Metallurgical problems are described quite well in the Poirier and Geiger book from TMS, the book titled Transport Phenomena in Materials Processing, and it has a lot of data also for the properties and tabulated values for different quantities that you will be looking for. So you can refer to these books for relevant problems that you may want to understand while going through this subject.